Hi, I'm Joseph Probante and I'll be reporting about transmission lines. A transmission line is a specialized cable or other structure designed to conduct system elements which carry signal power. It is also a means of conveying information from one point to another. There are two types of transmission lines, the unbalanced circuit and the balanced circuit. The balanced circuit has no grounded path, while the unbalanced circuit has one path being grounded. For the balanced circuit examples, we have two-wire open lines used in power lines, rural telephone lines, with the advantage of simple construction and low cost, and as disadvantage of highly susceptible to noise because of lack of shielding. The next one is a twin LED. It's like the same of the first example, used to connect television set to antenna, but is much better because of the shielding of low-loss dielectric material. The one in the figure is a two-wire ribbon type line. The next is a twisted pair used in computer networks and telephone sets. It has two types, the UTP and the STP, where the UTP is unshielded twisted pair and STP is a shielded twisted pair, being the shield as the ground. This is the formula for the balance line of characteristic impedance, where D is the distance between two conductor centers, R is the conductor radius, and K is the relative permittivity of insulation between two conductors. For the unbalanced line, we have the rigid coaxial line with advantages of minimized radiation losses because of good shielding and a disadvantage of expensive to construct and must be kept dry. It has the inner conductor that serves as the main conductor and outer conductor. It has also a washer to insulate the metal conductor. This is the characteristic impedance formula of a circular line, conical line, which has D1 as inside diameter of the outer conductor, D2 as the outside diameter of the inner conductor, and K as the relative permittivity of insulation between two conductors.
My name is Matthew Cabrera, and I will be discussing common losses in a transmission line. Three types of transmission line losses. First is the copper losses, second, dielectric losses, and third, radiation and induction losses. Copper losses. These are power loss in the form of heat or skin effect. It decreases the conductivity of a line. The power loss can be minimized and the conductivity increased by plating the line with silver. Skin effect means that the current that flows in the conductor is greater in the skin of the conductor rather than in the center of the conductor. Dielectric losses. These are caused by the heating effect on dielectric material between the conductors resulting to power loss. When there is potential difference, the orbits of the electrons distorts and the change in the path of electrons requires more energy, introducing a power loss. This can be prevented by using polyethylene as a dielectric because less power is consumed when its orbits are distorted. So this happens when there is charge and discharge in the conductors. Radiation and induction losses, both caused by the fields surrounding the conductors. Radiation losses. Some magnetic lines of force about a conductor do not return to the conductor when the cycle alternates. Lines of force are projected into space as radiation, and this results in power losses. Induction losses. An electromagnetic field about a conductor cuts through any nearby metallic object, and a current is induced in that object. Power is dissipated in the object and is lost. Length of a transmission line. A transmission line is electrically long if its physical length is greater than lambda over 16. Otherwise, the line is short. Example, a 10-meter line is electrically short at 1000 Hz and electrically long at 600 MHz. This can be evaluated by using this formula. Lambda is equals to V over F. I'm Matthew Cabrera and I will be reporting lossless transmission line. Lossless transmission line. No attenuation, no power loss. R is equals to 0, G is equals to 0. Energy supplied by a source at one end of such a line is transmitted to the line without being dissipated in the line itself. Wavelength, distance that provides a phase shift 2 pi radian, a measure of distance between two identical peaks, high points or throws, low points in a wave, a repeating pattern of traveling energy like light or sound. The formulas are lambda is equals to V over F, 360 degrees over beta, or equals to 2 pi over beta. V is equals to 2 pi F over beta, or equals to omega over beta. Complex propagation constant. So these are the formulas that are needed, and when reduced or simplified, omega over beta is equals to 1 over square root of LC, or V is equals to 1 over square root of LC. Input impedance for special termination cases. So Zin is equals to ZO times ZL plus J times ZO times tangent beta S all over ZO plus J times ZL times tangent BS. Case 1, ZL is equals to ZO or a matched line. So this is when the numerator is equals to the denominator. So they just cancel. Zin is equals to ZO. Case 2, ZL is equals to 0 or short-circuited line. The formula is Zin is equals to ZO, J times ZO tangent beta times S over ZO. Both ZOs of the numerator and denominator will be cancelled, and then the final formula is Zin is equals to J times ZO times tangent beta S. Input impedance for special terminations. For case 3, ZL is equals to alpha, open circuited line. By using L'Hopital's rule, this is the final formula. Zin is equals to negative J times ZO times cotangent beta S. And then ZO is equals to square root of ZOC times ZSC. ZOC is the open circuited line and ZSC is the short circuited line. Zin for special lengths. Case 1, S is lambda over 4 or quarter wavelength. By using the L'Hopital's rule, Zin is equals to ZO squared over ZL. Case 2, S is equals to lambda over 2, half wavelength. and the final formula is Zin is equals to Zl.
Good afternoon. Uh, the next session will be standing waves. My name is James I. Nunez of Group 1. So let's start. So standing waves, it happens when an incident wave reflects from a mismatched load. An interface pattern develops. And it also occurs between two waves moving in the opposite direction as each other with equal amplitude, wavelength, and frequency. So it's basically two waves that are the same that intersect with each other, causing um, a lesser amount or decrease of waves. So the formula is, as you can see here, a E1, uh, where E1 is the incident voltage and E2 is the reflected voltage, and computed with E raised to ZYS. At the load at S, or distance is equal to 0, is equal to EL, where EL is equal to the sum of the incident and the reflected voltage, or you can see here E1 and E2. So this is the standing wave representation, and also take note that the purple wave represents two waves moving in the opposite direction which are overlapping. Also note that when the crescent valley is of the two waves crossover maximum voltage is achieved, this is called antinodes. And also take note, when the waves are out of phase, the wave appears flat. This is like the gray line. These are called nodes. So nodes and antinodes, as in the figure above. So the nodes appear half wavelength, or lambda over 2, away from each other, and this is also true for antinodes. In total, a node and antinode are a quarter of a wavelength apart from each other, or lambda over 4, quarter wave. So reflection coefficient, a measure of the degree of mismatch between the load and the line, and also the amount of voltage reflected back, which is, the formula is equal to reflected divided by incident voltage, or the reflected current over the incident current, but the magnitude is, the polarity is different, or the direction. So from the equation standing wave, you can see here that the reflection coefficient can always be positive or negative depending on the phase, where also that if the load is equal to infinite, then at coefficient of reflection is equal to 1, it is open, and if it is 0, it is short. So the standing wave ratio, it is the ratio uh, of maximum to minimum current or voltage, and you can see here that the voltage standing wave ratio is defined as Vmax over Vmin, or Imax over Imin, as long as it's the ratio and it's related to the Ohm's law. And you can see here more formulas where it have coefficient of reflection and a standing wave ratio, and you can also see that they are all related.
My name is Julia Regala and I will be reporting about the position of voltage minima and voltage maxima. So S max is the position of the voltage maxima with respect to the load, and S min is the position of the voltage minima with respect to the load. So dito sa figure na to, we have a sine wave generator na nalagay sa isang short circuit. And then the broken line represents the voltage while the solid line represents the current. So dito at quarter wave points, yung voltage natin maging minima. For example, yung 1/4 wavelength and 3/4 wavelength. And then nagiging maximum lang yung voltage pag 1/2, and at one wavelength. So, since yung characteristic ng circuit natin ay yung series resonant LC circuit, yung mga shorted line natin, magiging inductance siya from 0 to 1/4 and 1/2 to 3/4. While magiging capacitance siya, mag-a-act siya as a capacitance sa or during, so 1/4 to 1/2 and then 3/4 to 1 wavelength. And to get the position, ito yung formula na gagamitin. And then to get S max, yung x natin magiging any positive integer, while S min is any positive odd integer. And then yung standing wave relation natin, pwede natin makuha through getting V max and V min and then divide lang. And then yung gamma. So for example, get the position for the first V max. So yung x natin na gagamitin is 0. And then substitute lang natin sa formula and makukuha natin yung value nito. Now for x min naman, since V min naman ang hahanapin or yung S min, gagamitin natin x is a positive odd integer. So substitute to x and then we will get this value. And then last step is to get the distance between S max and S min. So minus na yung nakuhang values kanina. And then yung result natin is a quarter wavelength.
Good afternoon again. I'm back and I'm here to talk about voltage and current at any point along the line. As you can see, this is a continuous solutions, so please bear with me. Okay, so let's start. So EL is equal to EI plus ER, as you remember earlier, right? So if we relate it to 1 plus coefficient of reflection, then continuously deriving the equations, we get that EG is equal to EL ZL plus ZO over 2ZL times the quantity of E square root of ZOS minus coefficient of reflection E raised to negative square root of ZOS. So continuing for current, this would be the same one. Let's just go back here. Oh, okay, so here we go to finally gamma is equal to square root of 1. So we substituted to Z in and then continuously deriving, we get this equation. Of course, recalling the trigonometric exponential identities is continuing, we get the final equation, which is Z in is equal to ZO multiplied by quantity of Z load plus ZO tangent H YS over ZO plus ZL tangent H YS for gamma S. So of course, if we manipulate tangent H gamma S, we get different cases, as you can see, with different alphas, distances, betas, and gammas. And this is, so the previous one was case 1, this is case 2. And then recalling Euler's identity from the earlier part. And then this is case 3, where alpha is 0, beta is 0, and gamma S is equal to JB beta S, which is a imaginary number. Okay, so continuing, making tangent H J beta S is equal to J tangent beta S. So transmission line input impedance, which is Z in earlier, the final formula, as you were able to see earlier also, which is commonly used in what we use today. Also note that cosine HJX is equal to cosine X and sine HJX is equal to sine.
Good morning, everyone. I'm Kyle Godinez, and here's my report for today, which is transverse electromagnetic wave. So first, the concept for a transverse electromagnetic wave is like an electromagnetic field that is a type of force that consists of an electric field and a magnetic field that came from the motion of an accelerating charged particle that has a quantized amount of electromagnetic energy. And this kind of field is evident along a transmission line as current travels on it. So for a transverse electromagnetic wave is where the electric and magnetic field lines are all restricted to directions normal, or is transverse to the direction of propagation. So from Maxwell's equation, using the spatial variation in the electric field E and is related to the time variation in the magnetic field B, and vice versa, we will see a result of the wave equation. So for the wave velocity, the velocity of a radio wave in a vacuum is equal to the speed of light, which is 299,792,458 meters a second. So for the medium of transmission has a contribution to the variation of the speed of the wave. We're gonna see it later for this table one. And for the wavelength, it's the distance traveled by a point in the time required to complete one cycle. So mostly it's like a sine wave for us due to the wave equation. Okay, so the frequency is the number of cycles per unit time. So velocity factor and relative dielectric constant. So the velocity factor is the ratio of the speed at which a wave passes through the medium to the light of speed of light in a vacuum. So for a different material that consists of the different velocity factor, there are different relative dielectric constant. So the dielectric constant or the permittivity is the property of a dielectric material that determines how much electrostatic energy can be stored per unit of volume when unit voltage is applied. So here's for the wave velocity is given v is equal to the speed of light over the permittivity constant or the dielectric constant. Okay, then we're gonna derive the velocity factor in it and the total velocity of the wave. So for the wavelength is given for the lambda is equal to the velocity over the frequency, where the lambda is the wavelength and v is the speed of the propagation along the line, and that is the frequency. So in an ideal space where the velocity factor is equal to 1, then we'll get the speed of light. Okay, 4 fundamental parameters in a transmission line is the capacitance, the inductance, resistance, and the conductance. So for the capacitance, it's just the capacitance between the two wires, and inductance due to stored magnetic energy. So as current travels to the inductor, it creates magnetic field. Then here's where the storage of energy happens. Then resistance is resistance due to the conductors because of its material property or its built. Then for the conductance due to the filling material between the wires. So when we coil the wire or we surround the wire with rubber or some other coating, this serves as a conductance. So characteristic impedance is the impedance measured as the input when the length of wire is infinite, also known as the surge impedance. So there's the transmission line equivalent circuit, there's the lossy line and the lossless line. So at radio frequency, R and G are ignored. Our line is considered to be